presentation, just continuation of the first part, okay? But please, every time you need to stop him, don't ask me, just...
Okay. So we left before. Are you well caffeinated? First of all, important question. Yes, I see. Resounding yes, so good. So I left you with like a cliffhanger before, right? Because said there were two questions to be answered before continuing. One was what flattening to use, and then with the help of the analog counter, which is not just those of the cassettes, as I was correctly suggested, pointed out, but also like in the cars when you count the kilometers that you have driven. And with a bit of discrete maths, we answered that the first question is it doesn't matter, which is typically the best answer you can get because it doesn't matter, so you do whatever you want. But we're left with the second question because it still remains that we need to take these deltas, this product of deltas there, and turn them into a separated really equation. So we need to separate these variables there and then try to make a vector equation out of it. So that's what we're going to do now, what we're going to do next. So how we do that? First of all, let's assume, just for the sake of argument in the beginning, let's assume that the possible communities in which you can assign the nodes are just two. So one community or another community. And here, by the way, I'm going to interrogate you to see if you have been paying attention yesterday and the day before in a short while. So if that is the case, then what we can do, we can say, okay, we can treat these nodes as if they were spins, like an Ising model, okay? And then it just spin up or spin down. And then we say your community left and right, or +1 or -1 for the spin. But then two things here happen, like we can start noticing two things. If that is the case, one single delta, like this one over here, we can write it this way. So the delta of the community of node I and community of node J can be written as a half of the product of the spins of I and J, the spin-like variables, +1. You want to see why? Suppose that one is in community 1 and community 2, so up, down, +1, -1. If the communities are different, the product as I, as J is -1, because one of them will be plus and the other will be minus. -1 + 1 is 0, 0 divided by 2 is 0, and the delta of different variables is indeed 0. Now, suppose instead they are in the same community, then they are either both +1 or both -1, so their product is 1. It's positive. 1 + 1 = 2, 2 divided by 2 is 1, and indeed the delta of equal variables is 1. So, if we do that, we can start noticing that we can write a single delta like this. Then, the other thing that we need to note is that the product here contains all possible combinations of these deltas. However, we don't need them all. Why don't we need them all? We don't need them all because of transitivity of equality. So, you know, equality is the prototypical equivalence class, equivalence relation. And one of the properties of equivalence relations is transitivity. If A equals B and B equals C, then A equals C. Which means here we don't need to have all these products, all of them, but we can just make a chain of products. If we have from 1 to k, we can do 1 with 2, 2 with 3, 3 with 4, and all the way to k. Because if they are all true, then also all the other combinations will be true due to transitivity. So we start thinking now in these terms. If we do that, then suppose we want to compute what happens for k equals 3. So we just do basically like the brute forcing calculation for k equals 3. For k equals 3, we have 1 with 2 and 2 with 3. That's it. So we have 1/2 times the product of S1, S2 plus 1 times 1/2 times the product of S2, S3 plus 1. We get 1/4, 1/2 times 1/2. And then we have S1 with S2 with S2 with S3. There you go. Plus S1, S2, plus S2, S3, plus 1. Okay, but then, at this point, we can take this and we plug it in the hypermodularity equation. Because, you know, for k equals 3, we just are brute forcing the expression. So we have 1 over k factorial, there is 3 factorial because k equals 3 times m times the sum, the data tensor, and this expression here. Now note, when I move from here to here, I've taken this S2 squared and I removed it. Why did I do that? Because S2, like S1 and S3, is either plus 1, excuse me, is either plus 1 or minus 1. And either plus 1 or minus 1 squared is always 1, right? So if this thing is always 1, I just removed it. And then I remove this plus 1. Okay. So now I'm stopping and I'm starting interrogating. I told you I was going to do it. First of all, who was that was asking Jose yesterday about what happens in the Ising model if you actually consider 3 body interactions rather than separating them? Somebody was asking. Who was it? You were asking. That's what happens. That's literally what happens. So what happens is that you start from an actual, if it is a ferromagnetic interaction, then you can write it as a product of delta that stops at k equals 3. If that is the case, then you can write it like this, which means you can write it like this, with one difference, a factor of 2 difference. You actually need to multiply this by 2 and subtract 1 at the end. But it doesn't matter. It doesn't matter very simply for one reason, is that if this goes into an energy expression, the plus 1 at the end, it's introducing just a constant term, and you can shift the energy by a constant term and the results will be exactly the same. So if you're using a ferromagnetic Hamiltonian for an Ising model with 3 body interactions or 4 body interactions, etc., it separates like this anyway, like Jose showed yesterday. So we answer your question with a day of delay, but we did. And the other thing is that I taken this 1 and I removed it. So you see, so I have S3 that multiplies S1 plus S2 plus S1 S2. And I put 1 and 1 goes away. The reason why I removed the 1 is that if you put the 1 over here, this sum is over all possible combinations of 3 nodes there. But then all possible combinations of 3 nodes of B times 1 is literally summing all the elements of B. And the sum of all the elements of B, the data tensor, is 0. And now I'm asking you, why is the sum of all the elements of B equal to 0? Aha. You know the answer? No. You know the answer. No, you do. Okay. Back. Forward. B. This is B. And now you see the answer, right? Signed graphs. Somebody was saying something about signed graphs. This B over here is a higher order version of a generalized Laplacian. The sum of all the elements of B is 0 because the sum of the elements of each row of B is 0. So the sum of the elements of the whole data tensor B is the sum of the elements of one row, which is 0, plus another row, which is 0, plus 0, plus 0, plus 0, and it's 0. So that is kind of like a higher order version of a generalized Laplacian. This is why. So we remove the 1 and we remove the squares and we end up with this expression over there, which is good. However, this is the same, I just rewrote it over there. However, this S1 over here, because we are summing over the sum over there, all the elements, etc., is a dummy index. So you can call it whatever you want. So I say, since we have already an S3 over there, you know what? I'm going to call this S1 S3. So I'm replacing one S1 with S3. So if I replace S1 with S3, I can rewrite this expression here as 1 over 3 factorial m times the sum B and big S of 3, where big S of 3 is just a quarter times S3 that multiplies S1 plus twice S2 over there. So this thing over here. Now, this S3 object separates the variables because you have S3 on one side and on the other side you have S1 plus 2 S2. And this is inside this expression here, multiplied by the data tensor, and summed over all the possible elements of that tensor. So you see, we are getting there, we are getting somewhere, but this is just for 3. Right? So for 3, we can write that the hypermodularity is literally this, where S transpose is the vector of the assignments of which community I put each node, which is n, dimension n, and on the other side, I have this sigma 3, which is a 2-dimensional, n-squared dimensional vector, whose elements contain the values of this expression here, so S1 plus 2S2, the values of S1 plus 2S2 for all possible pairs of nodes, including the repetition. So the first element will be S1 plus 2S2, where 1 and 2 are node 1 and 1. The second element will be S1 plus 2S2, when the two nodes are 1 and 2, and then 1 and 3, and 1 and 4, and so on, and so on, and so on. So for k equals 3, it works. We can actually separate the equation. But what happens? Can we separate it for the other values of k? So let's do something, and we repeat the same calculation. Now, I'm not going to go through the details. I'm just going to give you the results, and the results are here. The details are kind of like exactly the same. You take the product, you remove the squares, dummy indices, remove the plus 1 at the end, and you get this. It's 3, the one we just did, 4, 5, and 6. Well, so you look at it this way, and it's like this kind of uglish, but then you start noticing that there are patterns that are emerging. For 3, we have 1 over 4, which is 1 over 2 to the 2. For 4, we have 1 over 2 to the 3. So 1 over 2 to the 4 minus 1. 1 over 2 to the 5 minus 1. 1 over 2 to the 6 minus 1. Okay. 3, 3, 4, 4, 5, 5, 6, 6. Okay. And now look at this expression here. The one that separates the variables on the right-hand side. When the first, there are these little polynomials inside here. Where the first variable is S1, the factor in front of S1 is 1. When the first variable is S2, the factor is 2. When it's S3, it's S3. This is regardless of how many terms you have in that monomial. S1, S2, S3 starts with S1, so the factor in front is 1. There you go, S2, S4, S5 starts with S2, the factor in front is 2. S3, S4, S5 starts with S3, the factor in front is 3. 1, 2, 3, 4, 5 starts with 1, the factor before it is 1. We have an indication of something happening there. Not only that, when we have 3, this term here, from a point of view of discrete mathematics or combinatorics, is the list of all the sets of one element out of 2 possible choices. When we go to 4, you have still one element out of 3 choices. One element out of 2, so one element out of 3 minus 1, one element out of 4 minus 1, which is 3, and oh, look, new piece appears. 3 elements out of 4 minus 1. The next one is still 1 element out of 5 minus 1, 3 elements out of 5 minus 1, which is 4. And now we go to another one, which is even, and we have again 1 element out of 6 minus 1, 3 elements out of 6 minus 1, and we have 5 elements out of 6 minus 1. So we have 3, we remain with this. The next one is even, we have a new type of set that comes up. The next one is odd, the types of sets remain the same. The next one is even, a new type of sets pops up. Every even number, you have a new type of set that pops up. The choices are always k minus 1, and the types of sets are always also the odd choices out of k minus 1 possible choices. 1, 3, 5, 6 minus 1, 6 minus 1, 6 minus 1. So this means we can write down a generalized analytic expression for this. Because in all cases, sorry, what?
I have to admit that you have to be very contorted at the pattern the way you see it. It took your time at least, hopefully, or you just saw it immediately.
This, I'll tell you immediately, this one,
Years
No, this took me about 3 months.
3 months.
Yeah, about 3 months. This part here. So basically, we can generalize the whole thing. The hypermodularity, we have 2 to the k minus 1, k factorial m is from there. This is the same as before. On the left, we have a vector with n nodes, which is the assignment. And on the right, we have now, instead of sigma 3, we have sigma k, because it's the generalized one. This has n to the k minus 1 components. Each of one consists of the value of those expressions here on the right, but computed on a particular combination of nodes, like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, etc., etc. In turn, this means that these elements of the vector, we can order them. Again, the same trick here with the basis of the numbers is always the same. You see, right, 1, 1, 1, 2, 1, 1, 1, 3, 1, 1, 1, n, 1, 1, 1, then 1, 2, 1, 1, 1, 2, 2, 1, 1, 1. This is called inverse lexicographic order. It means like if you open a dictionary, this is the opposite of the order that you will see in a dictionary. So we are, by the way, lexicographic ordering is something that pops up continuously in graph theory. I don't know, are you familiar with the Fulkerson theorem? No? Okay. Never mind then. Look it up. It's suppose I give you a sequence of pairs of integers. Can this sequence be the in degree and out degrees of a directed network? Yes, no. Answer is you check it with the Fulkerson theorem, and you can simplify the Fulkerson theorem by rewriting the degrees in lexicographic order. And this gives you a test that is n squared, and then later on, I mean, you can prove some other theorems, and you can show that you can make also that test sublinear. Anyway, again, based on lexicographic ordering. So, you know, you write it this way. But if you can write it this way, this means that you have, in a sense, a way to address which element of the vector is which based on the patterns that we have identified, gives us literally an analytic expression for that, which is this. So if these, the xc1 to xk minus 1, are the indices that identify the specific element of the sigma k vector, I forgot the k, this is sigma k or whatever, or the sigma k vector, then you can write this as the sum over all the sizes r from 1 to k minus 1 that are odd, remember they were always the odd ones, of the sum over all the possible R sets, so all the actually R choices because you include repetitions, all the possible R choices, sigma 1, sigma 2, sigma r, chosen from a set of elements which is zeta 1, zeta 2, zeta k minus 1 of the products of the elements you have chosen, like we were doing before as 2, 3, 5, you know, this is, what are these, multiplied by some number alpha, which in a moment I'll tell you what it is, but you have to do this and compute it on the particular position of this, I don't want to call it manifold because it's discrete, it's not continuous, where zeta 1 equals the spin-like variable of the node whose index equals the index of the first here equals the first of the indices that identify the element of sigma, where zeta 2 equals the spin-like variable of the node whose index equals the second index that identifies the element of sigma, etc., etc., etc. And this alpha 1 is the ordinal index of the first sigma 1. So that basically, if the first sigma 1 is zeta 1, so S1 in the examples before, then alpha 1 is 1. If it is zeta 2, then alpha 2 is 2. If it is zeta 3, then alpha 3 is 3. The red numbers that I was writing before. So this is literally like 2 for loops, one inside the other, and you have computed yourself your whole vector, the big sigma vector. But most importantly, you have separated the equation. You have literally separated it with one small vector that gives you your assignment on the left-hand side, one big vector that is this combinatorial vector on the other side, and your data tensor in between. Which means, literally, that then if you do the higher order SVD, the considerations were before, then you can find the best assignment by simply taking the left singular vector that corresponds to the highest singular value. Again, just like eigenvalues and eigenvectors, because you are guaranteed that that matrix is real and orthogonal. So it spans your Rn. You multiply it and you get the right thing, which incidentally is literally the proof of why in machine learning, in classification tasks in machine learning, higher order SVD has been working so super well. People are like, wow, it works amazing. It really, really works well. We don't know why, but it works amazing, but we don't know why. Now you know why. The reason is that it's not an approximation. It's actually the best choice you can make. It gives you directly the best choice. And the reason is that you can always separate the classification tasks or the variables in the classification tasks this way. This is why it works well in that case. But that's not what we care about. What we care about, again, is continuing about the community detection and all. So, well, so good. So we can start making an algorithm. How do we make it? Do a bisection like this. Why bisection? Because we were assuming the spin-like variables, desing and all, and repeat, and repeat, and repeat, and repeat. So then we can do stuff next to it. Okay, we should. In fact, we will see. But the idea is I take something and I split it in two. And I take it and I split it in two, and split it in two, and split it in two. Right? And unfortunately, this screws up everything. And the reason why it screws up everything is that suppose that I start from here and I end up with 1 and 2. Okay? One of the main ingredients of the proof before was that the sum of all the elements of B was 0. But the sum of all the elements of B is the sum of the elements of B for all the nodes that are inside here. Now, if I want to split this in two, and I'm summing all the elements inside here, the sum is not necessarily 0, because I'm taking only some rows and some columns of the original data tensor. And that was a key ingredient in the proof before. So, oops. Yeah, so you do the first bisection and then you end up kind of like screwed. So what do? We need to find a way to go around this other problem. How do we go around this other problem? Like this. Suppose that we have done the split here. We have split it into two communities. Then we take one of the two and we want to see if we can split it again. So if we want to split it again, let's see, how would the hypermodularity change? What is the delta Q, the change of the hypermodularity? Well, 1 over k factorial m, because it's always out of there, so it's always remaining there. And then we got two terms. The first term is just this. The sum of the elements of the data tensor corresponding only to this community here, times the product of deltas corresponding only to these nodes there in that community. So like, literally kind of brute forcing the equation, minus the sum of all the elements of the subtensor of this community here. Why so? Because we are taking this and turning it into something else. We are taking this, change color, make it blue, and turn it into something else, right? So if I'm brute forcing the contribution for the modularity of this piece here and this piece here, I need to subtract the contribution of the modularity that was due to this that I had before. But that thing there is just that sum of these elements over there. So I remove that stuff and I add the next thing over. So where does this bring us? We take the product of deltas and we rewrite it as before, with the the sk on one side and the other expression on the other side. However, now we must keep the +1 over here. So if we write it down, we're going to end up precisely like this, where we have svk, the last spin-like variables. Then we have this f, which is the polynomials, the ones with the colored numbers that we were seeing before, whatever they are, I'm calling them f over here. But then we always have a +1 at the end. We cannot neglect it anymore. Okay, so we take this thing over here, and it's kind of like annoying. We can do something, however, that is going to turn out to be pretty workable, pretty easy to do at the end once you see the result. Okay. The first thing to do is we're just going to open up the whole thing. So you see here, I'm doing b times s times f, and then again there is the 1. So I'm going to end up with this. I have here the sum with b times s times f, and then another 1, which was the 1 term over here, and then minus the rest. Notice that I have opened up the sums. These were exactly the same sums as before. Sum over all the possible combinations of v1, vk, s, v1, vk. I'm just writing them explicitly because it's going to be easier to work with in a few moments. Then, here, we have the same. Here, we can factor out the sum in the last two terms because they are the same. So we go and we put them together. We have 1 over 2 to the k minus 1 minus 1, what they call mixed numbers, I think they used to call in high school, right? So we end up with minus 2 to the k minus 1 over 2 to the k minus 1. Okay, fine. Then here we have 1 over 2 to the k minus 1 here, and 1 over 2 to the k minus 1 there, and we bring it out. We factor it out. Okay, see? Now we have this first piece and this second piece that has 2 to the k minus 1 minus 1. Okay, very good. Next thing we do, attenzione here, we take this sum over here and we turn it into a product of products of sums. Why this? Because the second repeated sum is going to be not over k, but over k minus 1 indices. And I'm going to choose particularly some dummy indices, I think I call them w here, and I'm going to put deltas in between. So what's going on here? Have a look here. This goes from v1 to vk of the sum of deltas over here, and then this b, of course, still has k indices. Okay? This sum of deltas, sorry, product of deltas here, is 1 only when v1 equals v2, etc., all the way to vk. So the only terms that are non-zero in now this giant product here are the terms where all these SV1, SVK are exactly the same. Okay, so this here, it's like really summing on one single index of these ones. Let this be VK. Then this is like sum over VK times the sum over W1 all the way to WK minus 1, and B goes from W1 to WK. So this is literally the same. I just expanded this thing in this strange way, but I'm literally just summing over the same stuff. So why am I doing this? I didn't remember that I just done the colors here to make it clearer what I was saying, but there you go, just did. See, the only terms that are non-zero are the when the indices are all the same. So yes, this is effectively Lebesgue-Stieltjes integral, because this is over distributions, on multidimensional Dirac delta. If you do a normal integral over some function times the Dirac delta, it gives you the value of the function at 0. If you do a Lebesgue-Stieltjes integral using as a kernel a multidimensional Dirac delta, you end up with the value of whatever else you have, whether it is discrete or continuous, it doesn't matter, computed on the point where all its parameters are equal, which is exactly what we were saying here and why this is the same. Okay. So you see the index is the VK, the one that is missing. So again, we're just rewritten something simple in a very complicated way, which normally it's pretty bad. So why do you want to do this? And the reason is that eventually this helps us in fixing the final result. The reason is this. Look at this thing here. Remember we said about where all the indices are equal. But this expression here, S, VK times F, etc., 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 what does it do when all the elements are equal there, when all the indices are equal? Remember how these look like? We saw them before. By the way, sorry, I should also point out that in all these, the plus 1 has disappeared. Now we don't have any more the plus 1 that was giving us problems before, which is the other reason why we did all this. But look at that expression. See, look at these things here. These are the things that we are considering now. What do they do when they are all equal, where all these indices are equal? Look at this. This is the sum over all the one choice out of 2. 1 choice out of 2 plus 3 plus 3 choices out of 3. 1 choice out of 4 plus 3 choices out of 4. 1 choice out of 5 plus 3 choices out of 5 plus 5 choices out of 5. Reminiscent of anything? Yeah, I see a strong yes somewhere. I hope it will be for more people. Binomial theorem, anyone? That's basically the binomial theorem. When all the elements are the same there, this gives you 2 to the k minus 1 minus 1. Pascal's triangle, those nice things there. But then, considering that this thing here is also only giving you contributions when all the indices are the same, and that the sum of this when all the indices are the same is exactly 2 to the k minus 1 minus 1, we can put 2 to the k minus 1 minus 1, but we can multiply and divide by 2 to the k minus 1 minus 1 by multiplying and dividing by this term here or by 2 to the k minus 1 minus 1. Because since they are the same, you are multiplying and dividing by the same number, you are multiplying by 1. So there you go. Multiply by s times f and divide by 2 to the k minus 1 minus 1 inside this second term. And this is the reason why we did all this mess and putting this whole big sum over there. Because we wanted to make sure that we could bring this other piece inside here. And the way to bring this other piece down there is to make it manageable, to bring it in a moment when you know how much that gives you, what number that gives you, which is when all the indices are the same, and so that's the trick where it comes from. So we put it there, then we have, this 2 to the k minus 1 here and here cancel, they disappear. Then we take s and we bring it out here because we have s, and we bring it out to the left, and we have s over here, bring it out to the left, and we have f, and we bring f to the right, and we end up with this. S on the left, b minus product of deltas times the second sum times f, and the first sum is also out because nothing depends on it, nothing else depends on it. This thing here sums over all the possible spin-like combinations of the nodes, all of them, which means that inside here you are still considering all the elements of the community subtensor, all of them, which means that since the variables are separated once more, this is again a vector equation like the previous one, just exactly like the previous one. Precisely. Just the difference is that the matrix in the middle is no longer the flattening that we had before, but it is the flattening of a modified community subtensor. So it's a community subtensor that doesn't really have the normal, the same elements as before, but in some cases the elements are corrected. Now the good thing of this is the deltas. They are still saving the day, because this term here is non-zero only when all the k elements here are exactly the same, which means the only correction happens on the main hyperdiagonal of the community subtensor. Only when all the indices are exactly the same, you subtract this expression. Otherwise, you don't have to do anything. Good news. Why is it good news? Because it doesn't depend on k. Regardless of the dimension of your higher order network, you still only have to correct n elements. This is, again, a correction of O of n, not O of n to the k or some like a factorial or something like this. So it's a small correction, and this is good. Not only that, if you haven't yet divided the network, if you are like this, in the very beginning, that correction is identically zero. It vanishes, which means you don't even need to have an if in your program. You don't need to say, if number of bisection is greater than 1, then apply the correction. No, just compute it directly. Because at the initial stage, it's going to give you 0, so nothing's going to change. And it's still only O of n. And just n operations over something that is a little bit more messy than n, it's not going to be a big deal. So this saves the day, this whole calculation for the repeated bisection. Then after that, you say, okay, fine. After that, you hit on different problems. And the first problem is that if you are just bisecting, you are biasing, in a sense, your results. So you are biasing your results like you're getting wrong stuff. But effectively, you are giving a preference to a structure that can be done by, well, doing this. Eventually, see, here I stop and here I stop. It still looks like something where the pieces are still divided by 2, not necessarily two equal parts, but still divided like this and like that. So what we can add here is some traditional approaches, such as refinement, kind of like taboo search. I will be more precise later. And in fact, I'm going to show you that you can do easily 3 levels of refinement. One is a local refinement on the level of the nodes. The other one is a global refinement on the level of the nodes. And the last one is a global refinement on the level of the communities. So let's start with the local one. So how do you do it? The local one means you do the split. Any split, this one, it doesn't matter. As you have done the split, you have taken some nodes and you go like, you go here, you go there, you go there, you go here, you go here, you go there. And you stop, okay? Then you say, all right, suppose I take each node and say I assigned it to the left, and instead I say, no, now you move to the right. Or it was on the right, and say, no, now you move to the left. And I do this for every single node, and I compute, I write down, if I did that, how much the hypermodularity will change. So if I do this, it increases of a bit. If I do this, it decreases a lot, etc., etc. Then, when I have evaluated all the possible moves, I do the move that increases hypermodularity the most. Now wait, you do it also if the hypermodularity decreases. In that case, it's like will be the least negative decrease is still like the biggest increase is the least negative decrease. Even though it's bad, in principle it's bad, you still do it. Okay. Once you have done that, you block that node and you repeat the procedure. So there were n, now you repeat it again. Okay, there's n-1 nodes. If I move you here, if I move you there, etc., 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 which is the best move, even if it decreases the hypermodularity. Do it, and so on, and so on, and so on. All the way to the end, when every node has been swapped. Now, if you think about it, whether I call this one left and this one right, or I call this one right and this one left, it doesn't matter. So if I start like this and I end up the other way around, I'm going to end up with the exact same hypermodularity that I started with. However, what happens in between is a different matter. One thing that could very well happen, and moves here, is that say I start from here and I do something like this. And then at the end, I reach again the same point where I started. So this is why you need to accept in the beginning also moves that are bad. Because you may be going down some local minimum and then you will reach another maximum later on. This is why I said it's a sort of taboo search. Okay? So once you have done all this, you check in all the middle points which one is the middle point with the highest change in hypermodularity, and if it is positive, you accept it. So in this case here, bam, you put your network, your partition in this state over there. And then you repeat. So it's a decisional tree, and then you repeat, and then you repeat, and then you repeat. So the question is, how do you compute the change in hypermodularity? Now that's a different matter. So suppose you take a single node and you move it from one community to the next. So the vector S, the one with n components, will change in only one single element because it will change the sign, either from +1 to -1 or vice versa. The vector sigma, the combinatorial vector on the right-hand side, also will change only in all and only the elements that consist of combinations of nodes that include the one that you are moving. So we can write something like that. S goes to S prime, that is S plus delta S, and sigma goes to sigma prime, that equals sigma plus delta sigma. Now, delta S is 0 everywhere except its ith element, which is -2 times the original value of the spin-like variable, because it has to go from -1 to +1 or vice versa. So, after moving a node from one community to the other, the modularity, hypermodularity of the new partition is going to be this. Combinatorial factor in the beginning, the new vector S which is S plus delta S, times the flattening of the modified community subtensor, times the new vector sigma, which is sigma plus delta sigma. But now here we can actually do the products in this, the product here. So you have like S times E prime times sigma. Then you have S times E prime times delta sigma. Then you have delta S times E prime times sigma, and delta S times E prime times delta sigma. However, this term over here, multiplied by the combinatorial factor out, is literally what the hypermodularity was before we did the switch, because it's the vector S on the left and the vector sigma on the right. So that is the hypermodularity. So which means that delta Q, the change in hypermodularity, is this thing here minus this piece, which means it's only the remaining 3 pieces over there. Okay? So the remaining 3 pieces over there are here. And then we have here, it is S times C times delta sigma times E times sigma, and delta S times E times delta sigma. This plus this together, if you look at it, is like S plus delta S times E times delta sigma, which is S prime times E times delta sigma. So this tells you the change in hypermodularity, and it's kind of very convenient. Why is it very convenient? Because sigma, we already know it. We already know it because we computed it before when we did the split. We had to do, with the big thing, with the combinatorial expression of the sets, the choices or whatever, out of 5, out of 7, etc., etc. So sigma, we already have. So this thing here, this term here, is literally just, by the way, because this delta S, the change of S, this is literally just the ith row of E, okay, times sigma multiplied by minus 2S. And again, because the vector delta S, as we argued before, is literally 0 everywhere except in its ith element, which is minus 2 times Si, the value of the spin-like variable for the ith node. And this here, this delta sigma over here, only contains all and only the combinations of node I. So it's just literally a few terms, and you can compute it. That's it. Then the global refinement is basically the same, meaning, suppose we have done this. So we evaluate the split of this, and then we do the changes. We evaluate the split of this, we do the changes. When we have finished this sequence, we consider every single node and consider moving every single node from its current community to any other community that already exists, or to a new community that is initially empty. So I take it and I put it in an empty community, and just, repeat the same. This type of optimizations, by the way, which is an interesting historical thing, are sometimes called Kernighan and Lin optimizations, from the names of Brian Kernighan, who was the guy that invented the C programming language, and Shen Lin, that was his PhD student. And their original reason of inventing this, that now is just an optimization step, was to do community detection in networks. So they were doing community detection in networks, basically by kind of doing a brute force-ish taboo search. And it was like 1970 or something like that, I don't remember precisely. Now we use this same technique for optimization for NP-hard problems. I should have mentioned, this is actually an NP-hard problem. So this, like any other algorithm like this, will always be an approximation, will not be exact, except if P equals NP, and et cetera, et cetera, et cetera. So how do we compute here the change of hypermodularity in the case of the global refinement? So we are moving node I to some community alpha. Again, there will be 2 pieces here. One piece will be negative and would be consisting of contributions coming from all and only the combinations of k nodes that are in the original communities, and of which at least one of them is I. So it's like I plus other terms, or I plus other terms there. Why negative? Because we are taking I and we are moving it from here to somewhere else. Remember, in the hypermodularity equation, there's these deltas. So the only thing that matters is if everyone is in the same place. So if I originally is in this place here, you only need to consider I and everyone else that is in the same place. But you are moving it away, so all these terms will be negative. And then you have a bunch of positive terms, which will be all the combinations of k nodes in the new community in which you have temporarily put I, and then you, again, for the same reason, because those before didn't count because I was away, now I is here, and they count. All of these terms, then you just sum over the corresponding elements of B, because again, the formula is still 1 over k factorial m, etc., times the elements of B. Yeah, there you go, 1 over k factorial, I even wrote it, with the correct sign, plus or minus, depending on the contribution that it is. So again, just literally just that. Finally, the last thing is, suppose that we have done this, we have done the splitting, we have evaluated, we have moved the stuff. How about we put communities together? Take entire communities and boom, put them together. This is effectively what is called also the Louvain algorithm, which is again one of the most famous algorithms for community reduction. We are using it here as a refinement step. So we take two communities, join them together, take two communities, join them together. Just here we are doing it in a Kernighan and Lin structure. So we consider every possible combination of two communities. We do the calculation as before, etc., etc. Pick up the best middle point, repeat, repeat, until there is no improvement. Again, this was, they used to use this literally for just as a single step community reduction. Now we use it as a refinement. So how do we do this? Again, how do we compute the change of hypermodularity? Similar to the global refinement as before, you need to consider, say, if you have alpha and beta, the two communities that you're trying to put together, you need to consider the changes that are given by all and only the sets of k different nodes, so that at least one of them was in alpha and at least one of them was in beta. Again, why? The only thing that matters is where everybody's in the same place. Bunch of people that were in the same place before, if we are joining them, are still in the same place. Same place here, we join them, are still in the same place. The only thing that changes is when someone was here and someone was there, they were in different places, so they were not contributing anything. And when we put them together, now they do contribute. This is why you need all and only the combinations of nodes, such as at least one was here and at least another one was there. Sum all the corresponding elements of B, divide by whatever the combinatorial factor, and that's it. How do you do this efficiently? If you think about it, if you have whatever C communities, the change is a C by C square symmetric matrix. Why symmetric? Because if I put together community 3 and community 5, it's the same as if I put together community 5 and community 3, so it's kind of like the same. Now, suppose you accept a move, put community 3 and 5 together, all you have to do is you have to take the labels, the community labels of the nodes that were in community 5 and change them with 3. So we say 5, 5, 5, 5, and now we are 3, 3, 3, 3, 3, and forget about the row and column number 5. Not only that, if you think about it, you only need to update half of the column number 3 all the way to the diagonal and half of the row number 3 up to the diagonal, because it's a symmetric matrix. So every time you update half a row and half a column and then forget about one dimension of the matrix, and then forget another dimension, forget another dimension, you shrink the dimensionality of the problem up to the end and repeat. And that's your final refinement. And so we do this, we need to check how it works. Works like this. She gives us some other, at least for me, interesting consideration. So one typical test you want to do is I put everything random and I see how it works. So I just did here k equals 3, k equals 5, and the different colors are different orders of magnitudes of the size of the networks. And these are Erdos-Shreni, Erdos-Shreni-like, meaning basically every possible edge exists independently of any other possible edge with probability p that is here on the x-axis. So one thing you can notice is that if this is 0.2 over here, you got 0.2 up to 0.2 for random networks. Okay, so I say for random networks, hypermodularity is never above 0.2. And then you say, whoa, wait a minute. Here I see 0.8, 0.8. And I say, yes, but these symbols here are filled, you see, whereas these symbols here are empty. What does it mean? Well, as you decrease the probability of connection, the probability that each edge exists, the network fragments. Eventually, the network no longer consists of a single connected component. And when that happens, when the networks no longer consist of a single connected component, I'm putting empty symbols. So on connected networks, which is what we started assuming from the start, which is what basically is inherently assumed as an assumption in all these, hypermodularity is never above 0.2. Then yes, it's true. If you apply it where you are not supposed to apply it on, then you can get results like 0.8. So I find this actually a fairly important point because I have heard for quite a while now, more than 10 years actually, maybe 15 years, a lot of people say, no, modularity is wrong because modularity does hyperfitting. No, sorry, that is not correct. Modularity does not do hyperfitting. There's people that have literally published papers saying, look at that, I'm taking an Erdős-Schrödinger network with probability of connection 10 to the minus 5, whatever I have right there, and hey, I get modularity of almost 1. Hey, well, hey, what a surprise. I mean, obviously, because if you have a network that looks like this, isolated node, isolated node, isolated node, isolated node, single link, isolated node, single link, and your algorithm modularity goes like, you are by yourself, you're by yourself, by yourself, by yourself, by yourself, you two together, you two together. The modularity of this is something like 0.95, something like this. Well, obviously you find values that are so high even on random networks because you're not supposed to apply it on these networks here. It's supposed to be connected because otherwise what you're going to do? If you have a disconnected network, apply it on the individual components, treat each individual component independently and see what you find. I'll tell you what you find. You find this. You find maximum 0.2. You say, okay, but it's still not 0. Any one of you plays board games, Monopoly or Dungeons and Dragons for that matter. Right? If you roll a die, you can get 1, 2, 3, 4, 5, 6. If it's a 20, 1d20, you can get from 1 to 20, okay, whatever, right? Now, what is the probability that if I roll a die 10 times in a row, I get 10 times 4? Fairly low. Objectively, it's fairly low. It's not 0. It's not 0. What is the probability that if I take a very large network with a non-zero probability of putting links, entirely by chance, these links will get distributed so that there are some modules that are more strongly connected than others, entirely by chance? Well, something that gives you, in the worst case, a modularity of 0.2. So this is what I call a physiological value of the modularity. This is why I completely disagree with the thing about the overfitting. I mean, that's the explanation there. So, in Italy we have a joke, like if you take a monkey in front of a typewriter, have you ever seen a typewriter? Yes, okay, good. A monkey in front of a typewriter, and you spend enough million years, eventually you get the Divine Comedy out of it. It's possible. Not going to spend a million years to do that, but So that's pretty much the same thing, right? If you're testing this on a very, very large ensemble of networks where the probability of putting links is not exactly 0, it's a good probability. Stochastic fluctuations can give you the presence of modules or communities like this. Are they meaningful? That's exactly the point. If you do it and you find a result that is around 0.2 or less, the answer is no, they're not meaningful, because you know that even in a random case you will find it. It will be meaningful if you have a connected network, maybe maybe even a dense one. Here, this point here is 1, it's 10 to the 0, so this is 1, this is like fully connected. So if you have something dense-ish around here, and you find modularity 0.7, then you are guaranteed that it's really meaningful, because, normally you wouldn't expect it there, something like this. So this is one single thing. Number 2, tested it on actual real data. And there's some interesting things to note here, in my opinion. These are data from primary school contacts, like contacts of kids in primary school, I think in America. And we can run this code for different values of k and see what happens. So this for k equals 2. And the colors here correspond to different years. The shades correspond to different classes. So you have gold, that is year 1. Brown is year 2. Purple is year 3. green is year 4, I believe, and blue is year 5, and red is the teachers. So you can see, you can even detect the separation between different classes, like this, and the teachers themselves. And you find results, these are actually fairly reasonable if you think about it. Because look, year 1 together, year 2 together, year 3 together. They separate even by class, not just by year, with the difference of year 3 that they are together. And the one class of year 4 is together with those of year 5. Again, this is actually fairly reasonable. I always say that, like, when you're really, really a small kid, 1 year of difference makes a lot of difference in the maturity of people. So it's kind of like makes sense that these are separated by year. As you grow, when you reach like year 4, year 5, in many cases, the maturity of people in 1 year doesn't much change anymore. And you have here a class of year 4 that gets clustered together with year 5. So it's reasonable, which is actually good because we are testing an algorithm here, right? So if we found something that was completely nonsense, I wouldn't go like, wow, I've discovered something really, really cool. I will think like, crap, the algorithm doesn't work, right? So the fact that it's actually showing you something that is not surprising is good news here. K equals 3, notice the network fragments a bit because the number of higher order links starts decreasing. We have, again, year 1. Now see a bunch of year 1 people go together with year 2. Year 4 and 5, now they're solidly together. And these are the poor people of year 3 that are still by themselves. I make a joke here. Usually I say that they consider that year 1 and year 2 are too young, too small for them to play with. And they are considered by the year 4 and year 5 people to be too young. So, bam, year 3 is like the worst. Isolated by themselves, no one wants to play with them, no one wants to be with them. K equals 4 starts getting interesting. So K equals 4, you see, finally, some people of year 2 get together with year 3, and then you have this. And that's cool, in my opinion. Year 1 with 4 and 5 together. So like, this actually got me a little bit, and like, okay, now this I don't know what it is. Then I started looking at links, and I found that these were like all kids of year 4 or all kids of year 5 and 1 kid of year 1. I said, okay. And I said, wait a minute. Year 4 and year 1, year 5 and year 1 is like 3 or 4 years of difference. So I went and I looked at some papers of sociology and I checked what is the average difference in age between brothers and sisters in the period and places where they took this data here. And it was like, bam, 3.5. I said, aha, I know what's happening here. This is like a group of friends of year 4 or year 5, and then there is the annoying little brother or annoying little sister that jumps and clings on them that wants to hang up with the older boys and girls, and they say, okay, fine, doesn't matter. Since this is a higher order interaction, it's not 2 by 2, one annoying brother or sister in 5 or 6 of them, they say, it doesn't matter, it doesn't spoil our games too much. And so they allow them in, and that's what it is. Then if we go to even higher order interactions, this completely fragments, so this is like really small. So there isn't much to say here, except again that you see mostly division by year, but again, really here the network is so small, so there isn't much. We can do the same game on high school. So here we have instead the different colors are topics of that they study and the different shades are classes. So we have brown is chemistry, green is biology, blue is psychology, and purple is mathematics and physics. So first thing here, again, entire separation by class, by topic and by class, with the exception of the scientists, well, I shouldn't say the scientists, the mathematics and physics people there, which is kind of cool because it vindicates the fact that people say that typically the mathematicians and physicists are nerds, they don't make friends, they don't make good social interactions. Not true. It's exactly the opposite. They are the only group of people that make social interactions between different classes, even though they're still separated by topic of study, but they're the only ones that are, between the different classes. So not true that we are the nerds. The other are more nerdy, okay? And then we increase the order, and we start seeing people getting together, chemistry, biology, and and something interesting. So I have a way, like I called this big community here with some terms, because I thought about it. I hope you will agree. I don't know, I mean, it's fine. I think these are the complex system scientists, the complexity scientists, because you have mathematics and physics here, and then you have psychology. Now, the mind is a complex system. No, I said Ludovico yesterday is the brain, it's a super complex system and whatnot. So I say that basically all these people study complex systems, just they use different tools. So their way of thinking is akin, and when the interaction becomes higher order, you start seeing that, and they get together. In Latin, there is an expression, it's called forma mentis, which literally means the shape of your mind. So they have the same forma mentis, the same shape of the mind. They are all studying complex systems from this point of view. Then we can increase the order of interaction, and we start seeing network fragmenting, and we start seeing the importance of some bridging nodes over here. Sorry. So you may have, for instance, here, I don't know, I can't read the number, 176, this node over here, that has some connection within its own group of mathematics and physics, but also has meaningful connections within the group of biology. So these are some bridging nodes that are basically bringing some pieces of a community together with pieces of other communities. Same thing here. There is this person here that is a chemist that has strong connections with 4 or 5 psychologists and so on and so forth. So again, it seems that bridging nodes are more important for higher order interactions than they are for pairwise ones. And when we increase the order of the interaction even more, we get this, and I think that this is the interpretation is completely unequivocal, because these are study groups. I mean, this is clearly study groups. Look at that. People studying together, people that study together, sometimes with the addition of others, people that study together always, and sometimes you see 1, 2, or 3 of these others come together with them, and so on and so forth. So, not really surprising, by the way, because meaningful interactions at even higher orders are very likely to be people that are studying together. You have a question? Microphone?
I have a question about the physics interaction between with the psychologists, and it can be due with because physics and mathematics have more incidence of psychological disease, so they want to study
Absolutely.
about it.
Absolutely, but this would imply that the psychologists are more prone to the exploitation of their patients, which will mean that probably they will not graduate or certainly not be allowed to exercise the medical profession. It's like, we don't really, we don't look well on doctors that say, let me get friendly with this person so I can study on them. It's more like med scientist than doctor.
Yeah, but this relationship is specifically friendly, or just I have a contact with that person?
Sorry, what again? I didn't.
No, the edges are friends. Or they have some interaction.
Okay, no, this is not necessarily friendship. That is a good point that you're making. This is just basically contact, as in, sorry? Yeah, contact. So it's just people that interact. If the interaction is friendship, if the interaction is exploitation, we don't know that. So yeah, in principle.
Or maybe
Yes,
invitation
in principle, it's
for
possible, yes.
It well may be that physicists and mathematicians,
Yeah.
they understand that they are fundamental for the society,
Uh-huh.
but they soon they will understand they will not make money
Uh-huh.
because the society is going to be poor.
Uh-huh.
They get depressed because they see the other
And the psychologists help them, okay.
society. For example, I always say that one should be paid for the contribution is giving to the society. Now, Gandhi is giving to the society much better contribution than Cristiano Ronaldo. So I think that the salary of Gandhi should be at least the same as the one of Cristiano Ronaldo in a good society. This unfortunately is not happening. So Cristiano Ronaldo is depressed and they go to a psychologist to.
Possible? It is possible. Question there.
Do you have data about the gender or sex of these people? Because I'm married to a psychologist, and I'm not sure she's studying me, but maybe there is another interest there.
Okay, so, disclaimer, I do not want to be held responsible for any divorce or similar procedures, so I apologize if that happens. And to the best of my knowledge, the data were anonymized, so we do not know anything like, gender, actual age, or anything at all about that. No, you can assume, but it may be plus minus one because of variations. Sorry, yes? Not really, not really. I don't know.
China, the mathematicians are all women.
Yeah.
It's the opposite. I mean, if you go to Italy and in general Europe, mathematics physics is 80-20.
Not true.
80% is
No, not true. When I was a student, in my department of physics and in department of mathematics were like almost precisely 50-50.
you are a singularity because normally it happens this. I don't know why women are not choosing physics. That's another big question mark. But in general, it's very rare to have women entering the physics career, or at least in Europe. Then I went to China, and now I'm having several contacts with China. And in Chinese universities, exactly the opposite. Normally, you go to the physics department and the mathematics department is plenty of women. It's very rare to have a man.
That is true. I confirm. For China, I confirm.
Just come back into the psychology friendships with physics. Sheldon Cooper married a psychologist too, so he's very atypical. So
You mean
Sheldon
Glashow?
Cooper from The Big Bang Theory.
Sorry, I thought you meant, never mind.
So their anomalies behavior of a physics mind is maybe can
I
be
don't know.
interesting.
I personally know an actual physicist who also married a psychologist, but it's one. So this is not like, Yeah.
I see that this is
A
a topic.
topic, yeah. This is the classical type of topic goes on nature, if you think about it.
I know.
Yes.
Take out some stupid claim, but you can have some chance.
Have they tried to apply these hypergraphics and clustering to scientific collaborations networks?
I haven't. So I think maybe possible, right?
No, it's possible.
Yeah, I mean, so
Because you have,
the data from the archive.
we did a representation in terms of hypergraph.
Yeah, but not community detection.
No, not community
Eh.
detection, but it's possible because what you have is the data from archive, for example.
Yeah.
You have that nodes are scientists, then you have, for example, papers that are connections.
All right.
Now papers can be 2 authors, 3 authors, 4
Yeah.
authors, 5 authors. So all the papers with 2 authors are links. All the paper with 3 authors are hyperlinks of order 3. All the papers of 4 authors are hyperlinks of order 4, and so on.
Yeah.
So you can really map that into a. We analyze this in terms of
Distance, yeah.
but this is another thing. That probably, if you are interested, I will. So that's,
No,
that makes me that I now know what I'm going to present.
I'm going to talk about it. I was about to say, if you're interested in that, I'm going to talk about it, yeah.
I will do it at the conference.
Yeah,
I will talk about centrality and you will talk
about distance. Yeah, I already have, yeah. So, in, I think, Tuesday, Wednesday, I think I'm going to talk Wednesday about exactly about this.
Monday I will show you about centrality.
Perfect.
Are there more questions?
Oh, yeah.
So continue.
Nice questions. Plus, this is the end, so.
I have a very naive question. I don't know if it should be really wrong, but when you divide the clusters, right,
Yes?
why you couldn't just renormalize the B hypermatrices to become row sums equal to 0, to perform
Yes.
again.
Yes. Wait. As they say, it's blue. A picture is worth 1,000 words, because you may have this. You may have links between them. If there were no links between them, then yeah, absolutely, yes. Okay. But you cannot guarantee that there will still not. I cannot guarantee that there will not still be links between nodes in different communities. Yeah, I mean, hopefully fewer. Yeah. It cannot be 0, because if it were completely 0, disconnected components, right? In which case we end up with the problem as before. You're okay.
Quick question.
That's a Beatles t-shirt, isn't it?
Yes, it is.
Yeah.
That's a Despicable Me t-shirt, isn't
Yeah,
it?
yeah.
Quick question is about the algorithm that you use. What kind of network sizes can you manage? I mean, in reasonable times and stuff.
Yeah, so it depends, obviously, it depends on the order, right? So for lower orders, you can manage like even big ones, like for the lowest orders, I think you can go like easily million of nodes, like k equals 2 millions of nodes easily, k equals 3 probably more like 10,000 if you're running it on a single processor. Parallelization is a big mess here for 2 reasons. One, as I said, this is an approximation algorithm of an NP-hard problem, right? This means you don't want to run it a single time. If your system is very big, if your system is relatively small, okay, even thousands of nodes, with this level of optimization, you run it once and you get the best result the first time. Obviously, you should still run it many times, right? But you know, I have a code that basically I say run it whatever 1,000 times, and then it tells me I found the best result at attempt number, and invariably it's number 1. Okay. When the system is big, however, you really need to run it many times to be sure. And so basically you could parallelize it, but the truth is you also want to run it over and over and over again, as I said. And parallelization is not too easy because locality of reference is not enforced. So you're starting having a lot of communication between nodes, a lot of communication between cores. You cannot compact, you cannot tell the data structure to compact the memory. Now, sometimes operating systems do that by themselves. Linux, starting from 5 point, I forgot which version, tries every now and then to compact this type of memory allocations, but still you cannot guarantee it.
Yeah, and you answered my second question that it would be if you raise the order too much, of course you get very much more complicated, right? So if it's very order heterogeneous, it's just
yeah, right, that's the problem. So basically, it could be done, but it could be a GPU doesn't help.
Doesn't help.
I know it doesn't help, of course, because this is like if you have an Ising model on the GPU, you go like super lightning fast. But think about Bloom-Kapel model. You have holes there. So how do you run it on the GPU if you start having holes in between? This is not a matrix, it's a matroid, as we were saying before. The order is not guaranteed. It's not just a matter of locality of reference. So yes, GPU will give you some help, but it's not going to be that big of a help. So it's kind of like one of those nasty problems that you basically go like, I cannot do this, I cannot do that.
Thank you.
Maybe quantum computer, I'm joking. I'm joking, of course.
Very nice talk.
Thank you.
I have a question, which I don't know if it's an interesting question.
Every question is interesting.
So this hypermodularity and this whole approach to community detection is using a k-uniform hypergraph approach.
Yeah.
If you now try to generalize the hypermodularity to non-k-uniform graphs, could something be gained, or is this impossible?
Where is the home button on the Mac? Okay, sorry, I need to go back. I don't know how to get all the way to the beginning real quick. So, what happens if you try to do that are 2 or 3 different things, which are in reality connected. Uh-oh. Is it white also there? No. Okay, well, okay. Never mind. So remember the product of deltas there. So what happens if you are trying to generalize it to a non-uniform hypergraph is the same thing that happens if you're trying to generalize it to, it's literally, there you go, the same thing that happens if you're trying to generalize it to the situation where not all the nodes happen to be in the same community. What do I want to say? So here, this term here is 1 if all the k nodes are in the same community and 0 otherwise. Now suppose that we have like k equals 10, just to fix the ideas. Must we have all 10 nodes in the same community? In this formulation, answer is yes. But you could have 6. Let's say at least 6, if the majority is in the same community, then I accept this as a 1. Or you could have a combinatorial factor here that is proportional to the number of nodes being in the same community, stuff like this. Okay. That is the same as saying I may have here, the sum here, is not over all the combinations of nodes, of k nodes, but over all the edges, and the size of the edges can change. You will still end up with basically something here that is not guaranteed to have always the same shape, functional shape at the same time, which means that you cannot do this whole thing that we did here. That's the problem. So basically, you pay the price that you cannot do this. So there's someone who did exactly that with a different formalism, Bogumil, Kaminsky. He did exactly this, but with a different formalism. So instead of using a hypermodularity like that formula, he defined another modularity for hypergraphs, but based on Bayesian statistics applied to set theory. Now, if you actually take that and you apply it to k-uniform hypergraphs, you end up that the 2 formulae will give you the same number. So it's kind of like it's a dual formulation. However, because of the absence of the deltas there, but rather doing a probabilistic calculation, you cannot use this and you cannot do a spectral method. However, in that formulation, you, if you want, you can do different sizes of hyperedges. Yeah, you can mix hyperedges of different sizes, correct. Here, if you have hyperedges of different sizes, like in the examples before, you have to treat them all in a separate way. I'm not going to say that mine is right and his is wrong or vice versa, because again, I said this is an NP-hard problem. There's one behind and there's you. What, you had a question? Yeah, so someone behind with the hands, I couldn't figure out. You? No. Okay, then directly you have to resign. But basically this is the main the main problem there.
It's not a question, it's just comment, suggestion,
discussion.
Like there is a big debate in our community between hypergraphs and simplicial complexes. A lot of people use simplicial complexes because it helps publishing in Nature. Let's say like this. It's a nice.
Okay.
But simplicial complexes are very particular mathematical objects, are very particular hypergraphs. Yeah. And they're good mathematical objects because having a simplicial complex of order k implies that you have all k minus 1, k minus 2. So it's a sort of having some tensors with some internal structure, so certainly can help. It's a beautiful object mathematically, nothing to say. But in fact, in networks, I doubt very much that they have play a role. For example, when we were speaking of higher order interaction in social network, like you do, and we are speaking about group interactions. No, you're staying in a table, you put the cell phone, you're the only one without iPhone. When you go to a table, not necessarily you are a friend of each one of the other people staying in the table. So the fact that you are have an interaction with 10 people is not implying that you have one-by-one interaction with all of them.
And by the way,
or triangular interaction and so on.
yeah, by the way, this is my motivation for
Yes,
treating
exactly,
the things size by
exactly.
size.
So that's exactly. So I'm strongly against the simplicial complex. So now when I receive a paper on simplicial complex, I immediately reject.
Really?
Yeah, because it's no, if it's mathematician, I read. But if it is application,
Okay.
I want them to really justify why they use simplicial complexes. But now my question is, can this modularity measure help to understand how much simplicial is an hypergraph? For example, if you compare the modularity at different orders, can you guess how much?
Yeah.
Not that it's not simplicial 100%, because I mean, but you can say, okay, there are some higher order which imply the lower order, some other which does not.
Yeah, so I think
how much is the?
I'll give you the answer.
How much simplicial is?
So I give you the answer here, and I think actually the answer is fairly straightforward, and it is you could, but it's going to be like a lot of extra work when you can do the same thing in a much simpler way. It's going to be a lot of extra work because what you will have to do is you will have to build a correlation matrix between communities at different sizes, and then you check basically how close to one that is. It's like a lot of work. However, you can, if you have an interaction of size k, you know precisely, if it is a simplicial complex, how many interactions of size k minus 1 you should have, k minus 2, k minus 3, because it's just like basicest combinatorics, right? So why don't you look for them? You can just look for them and you consider the fraction of the interactions that you could have. So the fraction of interaction that you have over those that you could have or would have if it were a simplicial, kind of like a clustering coefficient. And you can call it simplicality coefficient, which is a horrible word, but you know, something of the sort. It's much easier. We make a paper on nature, of course. Much easier to, of course, much easier to compute than running this whole mess here.
Okay, if there are no more questions, let's thank the speaker and also all the questions. People make questions to enlighten the talk of today. Thanks a lot.